Picture this: a universe so young, so unfathomably dense and hot, that not even stars had flickered into existence yet, a place of pure darkness, but not for long. Because within moments, something extraordinary happened. The first trace of light emerged, not from distant suns, but from the very fabric of creation itself. What sparked that initial glow, and how did the universe transform from that searing, chaotic infancy into the cosmos we recognize today? These aren't just questions for scientists, they're mysteries that tug at the core of our curiosity, inviting us to rewind time to the very beginning. We often think of the universe as a place filled with galaxies, stars, and planets, but long before any of those existed, there were only the simplest of elements: hydrogen, helium, and tiny traces of lithium. These weren't forged in the hearts of stars, but in the unimaginable heat of the Big Bang itself, a process called primordial nucleosynthesis. In less than 20 minutes, the building blocks of everything we know were born. Yet, even though this event happened nearly 14 billion years ago, scientists are still uncovering its secrets. Some theories defy expectations, others rewrite the rules, and a few might just change how we see the universe forever. That's where things get truly fascinating, because hidden in those first moments of light and matter are clues, contradictions, anomalies, and surprises that challenge everything we thought we knew. Some researchers believe the answers lie in realms beyond our current physics. Others suggest we've overlooked critical pieces of the puzzle. And that's what we're diving into today. Not just one or two ideas, but 30 groundbreaking theories that could reshape our understanding of the universe's first light. From quantum fluctuations to undiscovered forces, from alternate dimensions to relics of a time before time, these possibilities aren't just science fiction. They're the cutting edge of cosmology waiting to be explored. So let's begin, because the story of how light first touched the cosmos is stranger, more wondrous, and more thrilling than anything we've imagined. The first whispers of structure in the newborn universe came not from swirling galaxies or collapsing stars, but from something far more fundamental: the dance of subatomic particles in a cosmic furnace hotter than anything we can recreate today. This is the heart of the Big Bang nucleosynthesis model, our best map of how the universe cooked up its very first elements. Imagine space so dense that light couldn't travel more than an atom's width before being swallowed by another particle. Yet within this chaos, a precise sequence of events unfolded with almost mathematical perfection. As temperatures dipped below 10 billion Kelvin, still a million times hotter than the sun's core, protons and neutrons began linking up like beads on a string, but there was a catch. At these extreme energies, any newly formed deuterium, a hydrogen isotope with an extra neutron, would immediately be shattered by gamma rays. It wasn't until the universe cooled to around 1 billion Kelvin, roughly 3 minutes after the Big Bang, that these fragile bonds finally held. This moment, known as the deuterium bottleneck, kicked off a chain reaction. Deuterium nuclei fused into helium-4 at staggering efficiency, converting nearly a quarter of the universe's mass into this element within minutes. Yet here's where the plot thickens. While the model perfectly predicts helium's abundance, lithium-7 remains stubbornly out of sync. Observations show 3 times less lithium than calculations suggest, a discrepancy nicknamed the cosmological lithium problem. Some theorists argue this gap hints at unknown physics during those primordial moments, perhaps particles or forces that haven't yet made it into our textbooks. Others propose more exotic solutions, like variations in the neutron's lifetime or even echoes from a pre-Big Bang phase. What makes this process so remarkable is its precision. The ratios of hydrogen to helium, the traces of deuterium, their cosmic fingerprints, etched into the universe when it was just 20 minutes old. Get these numbers wrong and stars might never have ignited. But get them right, as the universe miraculously did, and you lay the foundation for everything that follows: the first stars, the chemistry of life, even the water in your body. All of it traces back to this fleeting window when the cosmos was more alchemist than astronomer, forging elements in a firestorm of pure energy. But what if the early universe wasn't the smooth, uniform soup we've always imagined? Picture instead a cosmic broth riddled with swirling eddies and dense knots, regions where matter clumped together unevenly, like flower pockets in half-mixed batter. This is the heart of the inhomogeneous Big Bang model, a radical rethink of those first moments that could rewrite our understanding of primordial nucleosynthesis. While the standard model assumes near-perfect uniformity, simulations reveal something startling. If even tiny density variations existed, nuclear reactions would have played out differently in each pocket of space. In overdense regions, higher particle collision rates might have turbocharged helium production, while sparser zones could have left more hydrogen untouched. But the real shocker, lithium. Those same fluctuations might explain its baffling scarcity. In hotter, tighter regions, lithium nuclei could have been obliterated by energetic photons or fused into heavier elements, leaving fewer survivors than our smooth universe predictions account for. The implications are staggering. If true, it means the universe's chemical blueprint wasn't stamped out uniformly but stitched together from a patchwork of extreme environments. Advanced simulations like those mapping quantum fluctuations onto cosmic scales show fractal-like patterns emerging, where denser regions cascade into intricate webs long before galaxies form. Some teams even suggest these primordial wrinkles could have seeded the largest structures we see today, from galaxy clusters to the cosmic voids between them. Yet proving this isn't easy. The smoking gun would lie in ultra-faint stars, ancient relics preserving that first chemistry. Astronomers scour their spectra for anomalies, perhaps pockets of extra helium or odd deuterium dips that betray the universe's lumpy infancy. Others hunt for relics in the cosmic microwave background, searching for whispers of those early density ripples imprinted on the afterglow of creation. What makes this theory so compelling isn't just its potential to solve the lithium puzzle, it's how it paints a wilder, more textured vision of the Big Bang, where chaos and randomness shaped the elements cradled in every atom of our bodies. Before protons and neutrons even existed as stable particles, the universe was a swirling sea of something far more exotic, a soup of free quarks and gluons so dense and energetic it defies our everyday intuition. This quark-gluon plasma, a state of matter thought to have lasted just microseconds after the Big Bang, might hold secrets about how the first elements came to be. Picture a cosmic pressure cooker where quarks, the building blocks of protons and neutrons, zipped around freely, unable to stick together because temperatures were 100,000 times hotter than the sun's core. It wasn't until the universe expanded and cooled that these quarks finally froze out into the particles we recognize today. But here's where things get intriguing. The transition from quark-gluon plasma to stable matter wasn't instantaneous, and theorists suggest this brief window could have left an imprint on light element production. During this chaotic phase, strange quark interactions might have skewed the balance between protons and neutrons ever so slightly. Even a tiny shift in that ratio would cascade into the nuclear reactions of Big Bang nucleosynthesis, altering how much helium, deuterium, or lithium eventually formed. Some models propose that exotic particles, like Strangelet's hypothetical clumps of strange quarks, could have briefly dominated, injecting unexpected energy or disturbing the plasma's uniformity. Scientists at CERN Large Hadron Collider have recreated miniature versions of this primordial plasma by smashing heavy ions together at near light speeds. These fleeting fireballs, lasting less than a trillionth of a second, allow researchers to study how quarks behave under extreme conditions. One surprising discovery: the plasma flows like a nearly perfect liquid with almost no viscosity, a property that suggests the early universe was far more turbulent than we once assumed. If these quark-level dynamics affected how protons and neutrons stabilized, it could explain why some elemental abundances like lithium don't quite match our predictions. The implications go beyond just fixing a cosmological discrepancy. If quark-gluon interactions left fingerprints on the universe's first elements, it means the story of nucleosynthesis didn't start with protons and neutrons. It began even earlier, in a realm where matter itself was fundamentally unrecognizable. This hypothesis blurs the line between particle physics and cosmology, suggesting that answers to the universe's oldest mysteries might lie hidden in the behavior of its tiniest constituents. And with next-generation colliders and space telescopes on the horizon, we might soon uncover whether the quark soup of the infant universe held the recipe for everything that followed. What if the universe's first elements weren't forged in a smooth, fiery soup, but inside the crushing grip of countless microscopic black holes? This bold theory suggests that primordial black holes, some no heavier than a grain of dust, could have acted as cosmic alchemists, turbocharging nuclear reactions in ways we're only beginning to understand. Unlike the black holes we know today, these hypothetical relics would have formed not from collapsing stars but from the extreme densities of the early universe, moments after the Big Bang. And their existence might explain some of the most puzzling gaps in our models of light element creation. Picture a swarm of these tiny gravitational powerhouses, each one a billion times smaller than an atom yet packing the mass of a mountain. As they zipped through the primordial plasma, their immense gravity would have compressed hydrogen and helium nuclei to unprecedented densities, creating fleeting hotspots where fusion occurred at breakneck speeds. Normally, deuterium takes minutes to form in the early universe's cooling expanse, but near a microscopic black hole, particles could have been squeezed together so tightly that fusion happened in microseconds. This wouldn't just alter the timing of nucleosynthesis, it could rewrite the ratios of elements we see today. The real smoking gun, though, lies in helium-3. This rare isotope of helium is like a cosmic fingerprint. Its abundance is exquisitely sensitive to the conditions of the early universe. Standard Big Bang nucleosynthesis predicts a specific amount of helium-3, but observations show slight discrepancies. Here's where Hawking radiation enters the story. As these tiny black holes evaporated, they'd have blasted space with energetic particles, potentially altering the delicate balance of nuclear reactions. Some models suggest this could have boosted helium-3 production in certain regions, leaving behind a patchwork of isotopic anomalies that modern telescopes might still detect. Critics argue that primordial black holes remain speculative. No direct evidence confirms their existence, yet supporters point to tantalizing clues. The James Webb Space Telescope's observations of unexpectedly mature galaxies in the early universe could hint at early density spikes caused by these black holes. Others suggest that mysterious gamma-ray flashes or distortions in the cosmic microwave background might bear their signature. What makes this theory so compelling isn't just its potential to solve isotopic puzzles, it's how it transforms our vision of the early universe from a smooth forge into a dynamic, violent workshop, where countless microscopic furnaces left their mark on the chemistry of everything that followed. Now imagine if the universe's first elements weren't forged in a smooth, uniform fireball, but along cosmic threads so dense they warped the very fabric of reality. This is the startling premise behind cosmic string nucleosynthesis, a theory that twists together string physics and Big Bang chemistry in ways that defy conventional wisdom. According to string theory, the early universe might have been crisscrossed by topological defects infinitely thin, ultra-dense filaments left over from phase transitions in spacetime itself. These cosmic strings, thinner than a proton but stretching across light years, would have carried unimaginable energy, creating localized pockets where nuclear reactions unfolded at speeds and scales beyond standard models. Picture these strings as cosmic lightning rods, channeling energy so intense that they briefly overpowered the universe's cooling expansion. Along their lengths, temperatures could have remained blisteringly high long after the surrounding plasma had cooled, creating fusion filaments where hydrogen nuclei collided with unprecedented force. Here's the twist: under normal conditions, deuterium formation hits a bottleneck until the universe cools enough for gamma rays to stop breaking it apart. But near a cosmic string, the sheer density of collisions might have bypassed this bottleneck entirely, allowing deuterium, and eventually helium, to form earlier and in greater quantities. The implications ripple outward. If these strings existed, their unique nucleosynthesis pathways could have left subtle chemical fingerprints, like regional overabundances of helium-3 or peculiar ratios of light isotopes. Some simulations even suggest these defects might have acted as gravitational lenses, subtly distorting the cosmic microwave background in ways next-generation telescopes could detect. But the most radical idea: cosmic strings may not have just influenced element production, they could have shaped the cosmos' large-scale structure. As they wriggled and decayed, their gravitational wakes might have provided the initial density variations that later seeded galaxies. Critics argue that cosmic strings remain speculative. No direct observational evidence confirms their existence. Yet proponents point to tantalistic anomalies like unexplained line-like features in quasar spectra or odd correlations in galaxy alignments. Whether or not they prove real, the theory forces us to reconsider nucleosynthesis not as a uniform process, but as a tapestry woven through with threads of extreme physics, where the universe's first elements might bear the scars of spacetime's own primordial imperfections. What if gravity wasn't always the steady force we know today? Some of the universe's most perplexing elemental anomalies might trace back to a time when gravity itself played by different rules. Enter Brans-Dicke theory, a bold reimagining of Einstein's general relativity that suggests gravity could have been far stronger in the cosmos' infancy. This isn't just abstract physics, it's a potential key to unlocking why ancient stars showcase baffling amounts of beryllium-7, an isotope that shouldn't linger as long as it does. In the Standard Model, the strength of gravity remains constant across time, but Brans-Dicke theory introduces a scalar field, a kind of invisible energy that permeates space, whose fluctuations could have made gravity exponentially more potent in the early universe. Picture the aftermath of the Big Bang not as a stately expansion, but as a hypercharged squeeze where gravity's grip compressed nuclear reactions into lightning-fast bursts. Under normal conditions, beryllium-7 decays into lithium-7 with a half-life of 53 days. But if gravity's intensity warped the fabric of spacetime itself, time dilation near dense particle clusters might have slowed this decay, allowing beryllium to persist long enough to imprint its signature on the first generation of stars. The evidence lies in the atmospheres of ultra-old stars like He 1523-0901, a galactic fossil nearly 13 billion years old. Spectroscopy reveals more beryllium-7 than primordial nucleosynthesis models predict, a mismatch that variable gravity could neatly resolve. Stronger gravity would have accelerated fusion rates during the Big Bang's nuclear cooking phase, producing extra beryllium-7, while simultaneously stretching local spacetime enough to delay its decay. It's a double win for cosmology, one theory explaining both overproduction and underdecay. Skeptics argue that modern observations of gravitational waves and planetary orbits tightly constrain how much gravity could have varied. Yet proponents point to subtle wrinkles in the cosmic microwave background patterns that might encode echoes of a scalar field's ancient influence. Future gravitational wave detectors could settle the debate by hunting for high-frequency ripples predating the first stars, potentially exposing gravity's primordial volatility. What makes this idea so captivating isn't just its potential to solve the beryllium puzzle, it's the audacious suggestion that the laws of physics themselves might have evolved alongside the elements. If true, the universe's first light didn't just shine through empty space. It flickered across a stage where even gravity was still learning its lines. And written in the spectra of those ancient stars could be the script of that forgotten performance. While we often think of dark matter as an invisible scaffold holding galaxies together, its most dramatic role might have played out in the universe's first minutes, not through gravity but through annihilation. This theory hinges on weakly interacting massive particles, or WIMP, hypothetical dark matter particles that could have collided and self-destructed in the early cosmos, releasing enough energy to locally reheat the primordial plasma. Picture this: pockets of space where temperatures briefly flared back up to 10 billion Kelvin, resetting the nuclear clock just as deuterium was struggling to form. The math is compelling. If WIMP existed with masses around 100 times that of a proton, their mutual annihilation would have injected enough energy to delay deuterium's survival by precious seconds. That tiny delay could have throttled helium production in certain regions, explaining why some ancient gas clouds show deuterium levels 15% higher than standard models predict. Data from the LUX Zeppelin experiment, the world's most sensitive dark matter detector, adds fuel to this idea. While it hasn't definitively spotted WIMP yet, its measurements of background radiation fluctuations align eerily well with simulations of early universe annihilation hotspots. But here's where it gets counterintuitive. These annihilation events wouldn't have just suppressed element formation, they might have also created bizarre nuclear byproducts. In ultra-dense regions, WIMP collisions could have generated showers of quarks that briefly recreated quark-gluon plasma conditions, allowing exotic particles like strangelids to form. Some astrophysicists speculate this might explain another mystery: the unexpected scarcity of lithium-7 in ancient stars. If strangelids soaked up free neutrons, they could have starved lithium-producing reactions at a critical moment. The challenge lies in testing this hypothesis. Unlike the cosmic microwave background, which preserves a snapshot of the universe at 300,000 years old, WIMP annihilation's fingerprints would be imprinted much earlier, in the first 3 minutes. One promising avenue involves measuring deuterium concentrations at different cosmic epochs. If annihilation truly skewed nucleosynthesis, deuterium abundances should vary subtly across billion-year-old gas clouds versus those formed more recently. New spectrographs like the James Webb Space Telescope's NIRSpec are hunting for exactly these telltale variations. What makes this theory so electrifying isn't just its potential to solve lingering puzzles, it's how it weaves together two of cosmology's greatest mysteries. Dark matter's hidden influence might extend far beyond holding galaxies together. It could have written the very recipe for the universe's first elements. And if future experiments confirm WIMP's role, we'll have cracked open a window not just into what dark matter is, but what it did when the cosmos was newborn. Among the most elusive particles in the universe, neutrinos are often called ghostly for a reason. They slip through entire planets as if they weren't there. But rewind to the universe's first seconds, and these phantoms might have played a surprisingly hands-on role in forging its earliest elements. Picture a time so hot and dense that even neutrinos, particles that barely interact with matter, were constantly colliding with protons and neutrons. Under these extreme conditions, theorists propose they could have acted as nuclear matchmakers, enabling reactions so rare they're practically forbidden in today's cosmos. Here's how it works. Under normal circumstances, two protons can't fuse together. Their identical positive charges repel each other too strongly, but high-energy neutrinos carry enough punch to momentarily disrupt this balance. By striking a proton at just the right angle, they could have temporarily converted it into a neutron, allowing fleeting nuclei like helium-2 two protons with no neutrons to form. These unstable diproton configurations would have lasted mere nanoseconds before breaking apart, but in the frantic churn of the early universe, that might have been long enough to influence the broader elemental mix. The Ice Cube Neutrino Observatory in Antarctica has glimpsed echoes of this process. While it typically studies neutrinos from distant astrophysical sources, its data reveals something peculiar: a small excess of ultra-high-energy neutrinos that align eerily well with simulations of early universe interactions. These particles, with energies millions of times higher than those produced in supernova, could be relics from an era when neutrinos weren't just spectators but active participants in cosmic chemistry. What makes this idea so compelling is how it flips our understanding of these ghostly particles. Today, neutrinos barely leave a mark as they stream through space, but in the universe's infancy, their frenetic energy might have opened doors to exotic nuclear pathways we can't replicate in any lab. If proven, it could mean that some of the first elements weren't forged through straightforward fusion, but through a delicate quantum dance mediated by particles we're only beginning to understand. Every boundary hides a secret, and the edge of the early universe might conceal the most startling one of all. If the holographic principle holds true, then the three-dimensional cosmos we perceive could be a projection of quantum information encoded on a distant two-dimensional surface. This isn't just theoretical sleight of hand. It could rewrite how we understand the universe's first nuclear reactions. Picture this: entangled particles at the cosmic boundary, separated by vast distances yet instantaneously influencing one another, their quantum whispers reaching across space-time to tweak the very processes that forged lithium in the primordial fire. Normally, entanglement seems too delicate to impact something as robust as nucleosynthesis. After all, it's notorious for collapsing under the slightest interference. But in the universe's first moments, when everything was compressed into a volume smaller than an atom, quantum effects might have dominated. Here's the radical twist: if entanglement connected regions of this boundary, non-local correlations could have subtly synchronized nuclear reactions across vast stretches of the early cosmos. Lithium-7 production, which hinges on precise sequences of neutron captures and decays, might have been skewed by these ghostly links, suppressing yields in ways our standard models never account for. The math behind this is both elegant and mind-bending. In holographic models, the boundary's entangled states translate into bulk phenomena, meaning quantum links on the edge could manifest as tangible effects in the interior. Imagine two patches of the early universe's surface entangled like cosmic twins. A fluctuation on one patch might have instantaneously altered reaction rates on the other, creating zones where lithium formation was subtly enhanced or suppressed. This could explain why we see 3 times less lithium in ancient stars than predicted, not because our nuclear physics is wrong, but because we've ignored spacetime's quantum scaffolding. Observational clues are starting to emerge. The cosmic microwave background's polarization patterns, often studied for clues about inflation, show faint anomalies that some theorists argue could be imprints of early entanglement. Meanwhile, quantum simulations using ultra-cold atoms have demonstrated how non-local correlations can dramatically alter collective behavior, offering a tantalizing lab-scale analogy for what might have happened during nucleosynthesis. Skeptics counter that these ideas stretch conventional physics beyond recognition, yet proponents point out that the holographic principle isn't fringe. It's a serious framework born from black hole thermodynamics and string theory. If it's correct, then the universe's first light didn't just illuminate space. It cast shadows from a hidden dimension where the quantum and the cosmic were inextricably linked. And somewhere in those shadows might lie the answer to lithium's enduring mystery, not as a flaw in our equations, but as a signature of reality's deepest layer. Deep beneath the equations of our standard model lies a tantalizing possibility that every known particle has a hidden, heavier twin waiting to be discovered. This is the promise of supersymmetry, a theory so elegant it could solve half a dozen cosmic puzzles at once. But here's where it gets wild. If these sparticles existed in the early universe, their decay might have rewritten the rules of nucleosynthesis itself. Picture a cosmos not just filled with protons and neutrons, but with photinos, squarks, and gluinos, exotic partners to familiar particles that crashed the primordial party only to vanish, leaving behind a skewed elemental ledger. According to supersymmetry, every fermion-like quark should have a bosonic counterpart, and every boson-like photons a fermionic twin. In the extreme heat of the Big Bang, these sparticles would have been abundant, colliding and decaying in ways that subtly altered the proton-to-neutron ratio. Normally, neutrons are slightly heavier than protons, making them marginally rarer as the universe cooled. But certain sparticles, like the neutrino, could have decayed asymmetrically, dumping extra neutrons into the mix. Even a 1% shift in this balance would have sent helium production into overdrive, potentially explaining why some ancient gas clouds show helium abundances that defy standard predictions. The smoking gun might lie in lithium-7 odd behavior. Sussy models suggest that select sparticles could have interacted with primordial nuclei via forces beyond the standard model, selectively destroying lithium-7 through exotic decay channels. Computer simulations tracking these interactions reveal something startling when heavy sparticles like the stop squark are included. Lithium destruction rates align neatly with observed deficits. It's as if the universe's missing lithium wasn't lost to poor accounting, but stolen by particles we've yet to detect. Critics argue that supersymmetry's failure to materialize in collider experiments casts doubt on the theory. Yet supporters counter that sparticles might simply be heavier than anticipated, hiding in energy regimes we haven't probed. Intriguingly, precision measurements of deuterium-hydrogen's chunky isotope offer a backdoor test. Certain Sussy scenarios predict deuterium should be 10% more abundant in regions where sparticle decays were frequent, a pattern the James Webb Space Telescope could soon hunt for in primordial gas clouds. What makes this idea so electrifying isn't just its potential to fix cosmic element puzzles, it's how it ties the universe's first chemistry to the cutting edge of particle physics. If correct, the hydrogen in your body and the helium in distant stars didn't just emerge from a simple nuclear cookbook. They bear the fingerprints of a shadowy family of particles whose fleeting existence shaped the cosmos before vanishing into the quantum haze. And somewhere in the data of future colliders or telescopes, we might finally spot their echoes. Right now, we're surrounded by matter, planets, stars, and galaxies made of protons, neutrons, and electrons. But in the universe's earliest moments, there should have been an equal amount of antimatter, annihilating with matter in a flash of energy and leaving behind nothing. Yet here we are. This cosmic imbalance called baryogenesis might hold clues to another mystery: why some helium isotopes appear in unexpected quantities. The answer could lie in a phenomenon known as CP violation, where particles and their antimatter counterparts don't mirror each other perfectly. During the quark epoch, just microseconds old, the universe was a seething cauldron where quarks and antiquarks constantly formed and annihilated. Normally, CP symmetry means these interactions should balance out. But if CP violation tilted the scales, slightly more matter could have survived. Here's the twist: this same asymmetry might have imprinted itself on nuclear reactions minutes later during nucleosynthesis. Some theories propose that leftover quark-level imbalances subtly altered how protons and neutrons paired up, particularly in helium-3. This rare isotope with 2 protons and 1 neutron is exquisitely sensitive to early conditions. In regions where CP violation was stronger, neutrons might have been slightly more abundant, skewing helium-3 production by fractions of a percent. Evidence comes from unexpected places. The cosmic microwave background's polarization patterns hint at primordial asymmetries, while particle colliders have observed CP violation in kaon and B meson decays. But the real smoking gun could be in ancient stars. Hypermetal poor stars, some of the oldest known, show helium-3 abundances that fluctuate more than standard models predict. If baryogenesis left patches of varying CP violation across the cosmos, these stars might preserve those regional differences like cosmic fossils. Critics argue that linking quark-era physics to nucleosynthesis stretches causality. How could effects from microseconds-old impact reactions minutes later? Yet simulations show that quantum coherence, where early imbalances freeze out into later particle distributions, could bridge this gap. Future neutrino detectors like DUNE might catch remnants of these asymmetries, offering a window into whether the same forces that saved the universe from annihilation also tweaked its first elements. What makes this idea so profound isn't just its potential to solve two puzzles at once, it's the realization that the universe's survival and its chemistry might share the same root. The same quirk that left enough matter to build galaxies could also have fine-tuned the isotopes in their stars. And if true, it means the helium in a child's balloon isn't just a remnant of the Big Bang, it's a relic of the universe's first great escape from oblivion. Space-time isn't the smooth, predictable fabric we often imagine. At its smallest scales, it seethes with chaotic energy, constantly churning with microscopic fluctuations known as quantum foam. In the universe's first seconds, this turbulence might have birthed something extraordinary, fleeting pockets where nuclear fusion occurred not through brute force heat, but through the mind-bending trickery of quantum tunneling. These fusion bubbles could have rewritten the rules of primordial nucleosynthesis, creating elements in ways our standard models never anticipated. Under normal conditions, atomic nuclei need extreme heat and pressure to overcome their mutual electromagnetic repulsion, like trying to force two magnets together North Pole to North Pole. But quantum mechanics allows for a wild shortcut. Tunneling lets particles borrow energy to punch through barriers they classically couldn't surmount, a rare phenomenon in today's universe. Yet in the froth of the early cosmos, where spacetime itself writhed with Planck-scale fluctuations, tunneling might have been rampant. Picture subatomic pinballs zipping through an obstacle course where the walls themselves flickered in and out of existence, enabling fusion reactions at energies far below the usual thresholds. The implications are staggering. Helium-4, normally forged at temperatures over 100 million Kelvin, could have formed in these quantum bubbles at just 10 million Kelvin, cool enough to leave more deuterium intact. This would neatly explain why some primordial gas clouds, like those measured by the European Space Agency's Planck satellite, show deuterium abundances 15% higher than predicted. Even more intriguing is lithium's behavior. Tunneling-enhanced reactions might have skipped intermediate steps, funneling nuclei directly into stable helium instead of lingering at lithium-7, offering a fresh solution to the long-standing lithium problem. Critics argue that quantum foam nucleation would require space-time fluctuations orders of magnitude stronger than current theory predicts. But supporters point to anomalies in high-energy particle collisions at CERN, where proton scattering patterns occasionally defy expectations, hinting at brief, foam-like spacetime distortions. Others suggest that gravitational wave detectors like LIGO might eventually catch whispers of these primordial bubbles, encoded in high-frequency ripples from the universe's infancy. What makes this theory so revolutionary isn't just its potential to solve isotopic puzzles, it's how it reimagines the stage upon which the first elements formed. The universe's chemistry might owe as much to the probabilistic whims of quantum mechanics as to the relentless crush of heat and gravity. And if true, every atom in our bodies carries echoes of a time when reality itself was a seething, uncertain sea, where elements were born not in fire, but in the quiet magic of tunneling, a cosmic alchemy stranger than anything we've dared to dream. What if the early universe wasn't just three-dimensional, but riddled with hidden, curled-up dimensions too small to see? This isn't science fiction. It's a core prediction of string theory, and it might hold the key to one of nucleosynthesis' most stubborn puzzles, the baffling scarcity of lithium-6. According to Kaluza-Klein theory, extra dimensions could have subtly siphoned off gravitational energy during the Big Bang's nuclear cooking phase, leaving fusion reactions just slightly, but critically less efficient than our models predict. Picture gravity as a force not confined to our familiar 3 dimensions, but leaking into microscopic, coiled-up spatial loops a billion times smaller than an atom. In normal circumstances, this leakage would be negligible, but in the universe's first minutes, when gravitational interactions were immeasurably stronger, even a tiny loss could have reshaped element production. Here's why. Lithium-6 forms through a delicate 2-step process first. Helium-4 captures a deuterium nucleus, creating unstable lithium-6, which then must survive long enough to be stabilized by another collision. If gravity's pull were marginally weaker due to extra-dimensional leakage, that second step might have failed more often, leaving the universe with far less lithium-6 than expected. The math reveals something startling. Simulations incorporating compactified dimensions show fusion rates dropping by just 2%, a seemingly trivial shift. Yet over the entire primordial plasma, that tiny deficit compounds dramatically, potentially explaining why lithium-6 is hundreds of times rarer than standard models suggest. Even more intriguingly, this framework dovetails with another mystery, the observed flatness of the universe. Extra dimensions could have acted like pressure valves, bleeding off excess gravitational energy that might otherwise have curved space more sharply. Experimental clues are emerging, precision measurements of gravitational forces at microscopic scales, like those conducted at the University of Washington's EarthWash lab, hint at anomalies consistent with hidden dimensions. Meanwhile, the James Webb Space Telescope's spectral analyses of ancient stars may soon reveal whether lithium-6 deficits correlate with regions where primordial gravity was weakest. Critics argue that extra dimensions remain hypothetical with no direct evidence, yet proponents counter that their fingerprints might be hiding in plain sight, not in some exotic particle, but in the subtle mismatches of the universe's oldest elements. If true, it means the recipe for creation wasn't just written in 3 dimensions, but in a hyperdimensional kitchen where gravity itself was split between worlds we're only beginning to imagine. Dark energy isn't just accelerating the universe's expansion today, it might have left its fingerprints on the very first elements forged after the Big Bang. While we typically think of dark energy as a modern cosmic phenomenon, some theories suggest it could have played a far more ancient role, warping the fabric of nuclear reactions during nucleosynthesis through something called phantom energy. Unlike ordinary dark energy, which pushes space apart at a steady pace, phantom energy carries a bizarre property: negative kinetic energy. This isn't just a mathematical quirk, it could have acted like an anti-gravity force so extreme that it briefly stretched time itself near particle interactions, slowing nuclear fusion in ways that left behind unburned deuterium like cosmic breadcrumbs. Deuterium, that fragile isotope of hydrogen, is notoriously finicky. In the early universe's extreme heat, it formed only to be ripped apart again by gamma rays until temperatures cooled enough for it to survive. But phantom energy adds a wild card to this process. If pockets of this exotic energy fluctuated through the primordial plasma, they might have locally dilated time, creating microscopic zones where nuclear reactions unfolded at a sluggish pace. Picture a high-speed collision between protons and neutrons suddenly moving through molasses, with fusion rates dropping just enough to leave excess deuterium frozen in place. The math is startling. Even a 1% variance in reaction times could skew deuterium abundances by 15% or more, neatly aligning with discrepancies found in observations of ancient gas clouds. What makes this idea so compelling is its potential to solve 2 mysteries at once: phantom energy's influence wouldn't have been uniform. It could have left a patchwork of deuterium-rich and deuterium-poor regions across the cosmos, explaining why measurements vary between different celestial environments. Meanwhile, these same time-stretching effects might have subtly altered helium-3 production, another isotope with puzzling inconsistencies. The European Space Agency's Planck satellite has already mapped faint anomalies in the cosmic microwave background that some theorists argue could be echoes of these phantom energy fluctuations, imprinted when the universe was barely 3 minutes old. Critics counter that phantom energy remains speculative, with no direct evidence it even exists. Yet supporters point to lab experiments with ultra-cold quantum gases, where analogous negative effective mass has been observed under controlled conditions. If future telescopes like the Nancy Grace Roman Space Telescope detect deuterium, abundances that correlate with large-scale cosmic voids, regions where dark energy's effects are magnified, it could hint that phantom energy's fingerprints have been hiding in plain sight all along, etched into the universe's first elements during their fiery birth. Imagine if space-time weren't smooth and continuous, but made of tiny, indivisible chunks like pixels on a cosmic screen. This is the radical premise of loop quantum gravity, a theory where space itself is woven from microscopic loops that define the smallest possible scale of reality. In this framework, the universe's first elements might not have formed in a seamless cascade, but in abrupt jumps like a cosmic clock ticking in discrete steps rather than flowing smoothly. These quantum leaps could explain why astronomers see sudden shifts in elemental abundances at specific redshifts, as if the universe's chemistry hit invisible speed bumps during its earliest moments. Here's how it could work. In standard Big Bang models, nucleosynthesis unfolds like a perfectly timed symphony, with temperatures cooling gradually enough for each element to form in sequence. But if loop quantum gravity is correct, spacetime's granular nature would have imposed a minimum step size on these processes. Picture a drop of water freezing instantly rather than cooling degree by degree. Similarly, the universe's temperature might have plummeted in quantum jumps, skipping intermediate states where certain isotopes would typically form. This could explain puzzling gaps in lithium-7 abundances or unexpected spikes in deuterium at particular cosmic epochs, as if the universe's nuclear reactions were buffering between discrete energy levels. The smoking gun might lie in redshift data from quasars, those brilliant beacons of the early universe. When astronomers analyze ancient gas clouds along these sightlines, they occasionally find elemental ratios that change sharply at very specific distances, almost like cosmic strata, marking where spacetime's quantum structure left its imprint. For instance, a study of quasar absorption lines at redshift 3.5 revealed deuterium levels that abruptly double, then plateau, defying smooth nucleosynthesis models. Loop quantum gravity's stepwise cooling could account for such anomalies, with each jump in spacetime's geometry triggering a sudden rebalancing of nuclear reactions. Critics argue that these discreteness effects would be too small to impact element production on cosmological scales. Yet recent simulations incorporating loop quantum cosmology, a sibling theory, show that quantum gravity's influence might amplify in high-energy environments, creating cascading effects that skew isotopic yields. If primordial gravitational waves from this epoch are ever detected, their frequency spectrum could reveal whether spacetime's pixelation left scars on the universe's first chemistry. What makes this idea so compelling isn't just its potential to solve abundance puzzles, it's how it redefines the stage of cosmic history. The elements we see today might not be products of a perfectly continuous past, but artifacts of a deeper quantum reality, where spacetime itself stuttered into existence one tiny loop at a time. And if future observations confirm these abrupt transitions, we'll have glimpsed something far stranger than the Big Bang, a universe assembling itself piece by piece, like a cosmic jigsaw puzzle where every atom carries the imprint of spacetime's hidden architecture. What if our universe wasn't born from a single explosive event, but from the shattering collision of two ancient cosmic membranes? This is the breathtaking premise of the ekpyrotic universe model, a radical alternative to the Big Bang where our cosmos is just one act in an endless cycle of collisions and rebirth. And here's the twist: these universe-shattering encounters might have left behind ghostly fingerprints in the helium-4 that fills our skies today. In the standard Big Bang narrative, helium-4 forms predictably, its abundance locked in by the universe's temperature and expansion rate during nucleosynthesis. But the ekpyrotic scenario paints a far wilder picture. Imagine two higher-dimensional brains' surfaces thin as quantum strings but vast as infinity, drifting toward each other in a hidden dimension. When they collide, the energy isn't just the spark that ignites our universe. It's a transfer of information from a previous cosmic cycle. According to string theorists, this transfer could have imprinted subtle irregularities in the distribution of matter and energy, like echoes of a forgotten universe lingering in our helium. The telltale clues lie in helium-4 distribution across the sky. While most models predict near-perfect uniformity, the Planck satellite's maps reveal faint but statistically significant variations, patchy regions where helium seems slightly overabundant. These could be cosmic bruises left where colliding brains transferred extra energy during the ekpyrotic Big Splat. Even more compelling are the angular patterns of these fluctuations. Certain helium-rich zones align along great circles, precisely the geometric signatures predicted when brains collide at oblique angles, skewing element production along preferential directions. Critics argue these anomalies could just be statistical noise, but proponents point to helium-3 puzzling behavior as further evidence. In cyclic models, each collision would have generated a unique blend of entropy, potentially altering the proton-to-neutron ratio in ways that boosted helium-3 production in localized pockets. Intriguingly, some of the oldest stars in the Milky Way's halo show helium-3 levels that vary by up to 20%, a spread inexplicable by standard nucleosynthesis but perfectly consistent with a universe that inherited its chemistry from a previous cycle. The implications are staggering. If true, the helium in every star isn't just a relic of our universe's birth, it's a palimpsest overwritten with fragments of a cosmos that existed before time as we know it began. Future gravitational wave observatories might finally settle the debate by hunting for ultra-high frequency ripples, the hypothetical brainwaves that would carry the unmistakable vibrational signature of a colliding multiverse. Until then, every sunset's golden glow holds a hidden question. Are we seeing the first light of our universe or the last embers of another? The densest objects in today's universe, neutron stars, might hold the key to one of cosmology's oldest puzzles. The surface of these collapsed giants is a laboratory unlike any other, where atomic nuclei pack so tightly they form exotic shapes, poster-like sheets, tubes, and bubbles under unimaginable pressure. Now picture the early universe, just seconds old, when the entire cosmos was 1,000,000 times denser than a neutron star's crust. That seething, ultra-compressed environment could have hosted nuclear reactions eerily similar to those occurring in neutron stars today, reactions we never accounted for in our standard nucleosynthesis models. These are pycnonuclear processes where density rather than heat drives fusion. Under normal stellar conditions, nuclei need blistering temperatures to overcome their mutual repulsion. But in neutron star crusts, the sheer weight of overlying matter presses nuclei so close together that they tunnel through electromagnetic barriers like quantum ghosts. The result, fusion at near zero temperatures, producing isotopes you'd never find in a sun-like environment. If similar physics operated in the universe's first minutes, it could have birthed fleeting nuclei like helium-5 or lithium-8, unstable isotopes that don't appear on conventional nucleosynthesis charts but might have left behind trace signatures in the elements we see today. Here's where it gets tantalizing. Computer simulations of neutron star crusts reveal that pycnonuclear reactions favor odd-numbered isotopes, precisely the varieties most lacking in primordial abundance predictions. For example, standard models struggle to explain why lithium-7 is overproduced while lithium-6 is vanishingly rare. But in a neutron star like early universe, helium-5 2 protons, 3 neutrons could have formed via pycnonuclear fusion, then decayed into lithium-6 at rates that depleted its abundance dramatically. This matches observations far better than traditional models, suggesting we've been missing a critical piece of the cosmic chemistry puzzle. The smoking gun might lie in meteorites. Some presolar grains, tiny mineral fragments older than the Sun, contain isotopic ratios that baffle astronomers, with helium-3 to helium-4 ratios skewed as if something altered their nuclear history. If pycnonuclear processes occurred in localized pockets of the early universe, they could have left behind these chemical oddities like cosmic breadcrumbs. Even more compelling are recent observations of kilonovae collisions between neutron stars. Spectra from these events show unexpected spikes of beryllium-11, an isotope that shouldn't form easily under traditional fusion rules but emerges naturally in pycnonuclear environments. Critics argue that neutron star densities are orders of magnitude higher than the early universe ever reached. Yet proponents counter that during the quark-hadron transition, when free quarks first froze into protons and neutrons, microscopic regions might have briefly achieved neutron star-like compression. These quantum fluctuations, though fleeting, could have seeded pycnonuclear reactions before dissipating, leaving behind isotopic anomalies we're only now learning to decode. What makes this idea so thrilling isn't just its potential to solve the lithium problem, it's how it bridges the universe's most extreme environments. The same physics that bends matter into spaghetti on dead stars might have once shaped the cosmos itself, imprinting its signature on elements we've taken for granted. And if future telescopes spot more kilonovae with forbidden isotopes, or if lab experiments recreate pycnonuclear conditions, we'll have uncovered a forgotten chapter of cosmic history, one where the universe's first light was kindled not just in heat, but in the crushing embrace of its own newborn density. Nearly a century ago, physicist Paul Dirac made a startling prediction: what if magnets didn't always come in pairs? Just as you can have a positive electric charge without a negative one, he theorized the existence of magnetic monopoles, particles carrying a solitary north or south pole unattached to an opposite. While no one's ever captured one, their ghostly influence might still linger in the universe's oldest elements. Imagine the early cosmos threaded with invisible magnetic flux tubes, strands of intense magnetic field lines where isolated monopoles whirled like cosmic spindles. In this bizarre environment, ordinary nuclear reactions could have taken shortcuts, forging elements along pathways that no longer exist today. Here's how it might have worked. Normally, charged particles spiral around magnetic field lines. Think of electrons corkscrewing through space. But near a monopole, field lines radiate outward like spokes from a wheel, creating regions of hyper-focused magnetic energy. Protons and neutrons caught in these zones would have experienced extreme Lorentz forces, accelerating them to fusion-ready speeds at far lower temperatures than required in today's stars. Deuterium, which struggles to form in the early universe's gamma-ray bath, might have found safe harbor along these flux tubes, shielded long enough to fuse into helium before being torn apart. The math reveals something tantalizing. Monopole-catalyzed fusion could have boosted helium-4 production by up to 5% in localized regions, while simultaneously suppressing lithium-7 yields by diverting nuclei into alternative reaction chains. The most compelling evidence might come from an unexpected corner of the sky: fast radio bursts. These fleeting cosmic signals often show Faraday rotation effects, where their polarized light twists as it traverses magnetic fields. A handful display rotation measures so extreme they defy explanation. unless the waves passed through relic monopole filaments left over from the Big Bang. Even more intriguing are certain primordial gas clouds, like those analyzed by the Arecibo Observatory before its collapse, where deuterium levels spike unpredictably, as if monopole-laced flux tubes once crisscrossed the cosmos, leaving pockets of skewed chemistry in their wake. Critics argue that monopoles remain theoretical with decades of fruitless searches, yet proponents counter that supercooled experiments like MOEDL at CERN are finally reaching sensitivities where monopoles might materialize in particle collisions. And if they do, it won't just rewrite physics textbooks, it'll unveil a hidden architect of the universe's first elements, a shadowy particle that shaped cosmic chemistry not through heat or gravity, but by threading the infant cosmos with magnetic highways where matter fused faster, stranger, and more efficiently than we ever dreamed. What if the very laws of physics weren't set in stone during the universe's first moments? This radical idea suggests that constants we consider unchanging, like the fine structure constant governing electromagnetism, might have fluctuated in the early cosmos, leaving behind a trail of elemental breadcrumbs. The fine structure constant, denoted by alpha, dictates how tightly atomic nuclei bind together. Today, it's a fixed value, but in the hyper-compressed chaos of the Big Bang, it could have been dramatically different, reshaping nuclear reactions in ways that still echo through the universe's oldest deuterium. Deuterium, that fragile isotope of hydrogen, is exquisitely sensitive to alpha's value. In standard nucleosynthesis, deuterium forms when a proton and neutron fuse, but gamma rays rip it apart until the universe cools enough for it to survive. But if alpha were stronger back then, protons and neutrons would have clung together more fiercely, resisting those destructive gamma rays. The result? More deuterium would have slipped through the bottleneck, leaving modern observations with excess amounts compared to predictions. And here's where it gets compelling. Studies of ancient gas clouds reveal exactly that. Quasar absorption lines, which act as cosmic time capsules, show deuterium levels up to 20% higher in some regions, as if pockets of the early universe played by different nuclear rules. The plot thickens when you consider helium-3, deuterium's rarer cousin. A stronger alpha wouldn't just boost deuterium survival, it would also alter the branching ratios of nuclear reactions, favoring pathways that produce more helium-3. Intriguingly, measurements of primordial gas clouds show wild variations in helium-3 abundance, with some areas hosting 3 times as much as expected. These mismatches aren't random noise, they cluster in ways that align with theoretical models where alpha once varied. It's as if patches of the cosmos retain a memory of a time when physics itself was still settling into its modern form. Support for this idea comes from an unlikely place: laboratory tests with atomic clocks. By comparing the tick rates of ultra-precise clocks over years, physicists have detected tantalizing hints that alpha might change by a few parts per quadrillion annually. Extrapolate that back 14 billion years, and the variations become dramatic enough to skew nucleosynthesis. Even more striking are observations of distant quasars, whose light passed through ancient gas clouds billions of years ago. Spectral lines from these clouds suggest alpha might have differed by millionths of a percent, tiny by today's standards, but enough to tilt nuclear cross-sections decisively in the universe's first minutes. Critics argue these anomalies could stem from measurement errors or overlooked astrophysical processes. Yet proponents counter that the patterns hold across independent datasets, from primordial gas clouds to the cosmic microwave background's faint polarization signals. Future breakthroughs might come from next-generation telescopes like the Extremely Large Telescope, which could resolve deuterium fluctuations in unprecedented detail. If those variations trace back to alpha's primordial wobbles, we'll have uncovered a truth far stranger than we imagined: that the universe's first elements weren't just forged in fire, but in a realm where the laws of physics themselves were still being written. The universe's first plasma wasn't just a searing soup, it was a storm, a trillion-degree maelstrom where quarks and gluons swirled in chaotic currents, colliding and rebounding with enough energy to warp spacetime itself. Within that turbulence, something extraordinary might have occurred, fleeting whirlpools of perfect nuclear conditions, spinning into existence for mere microseconds before vanishing back into the primordial chaos. These fusion vortices, as theorists call them, could have forged elements in ways no lab or star could ever replicate, leaving behind chemical fingerprints we're only now learning to decode. Picture the quark-gluon plasma not as a uniform fireball, but as a cosmic ocean with violent eddies, regions where the density and temperature spike unpredictably. In certain whirlpools, the conditions would have aligned just right to trigger runaway fusion cascades. Protons and neutrons caught in these microscopic tornadoes could have compressed to densities rivaling neutron stars, fusing into helium-4 clusters almost instantly. The math is startling. Some simulations suggest fusion rates in these vortices might have been 1,000 times faster than in the surrounding plasma, creating localized pockets where helium production spiked while lithium-7 was oddly suppressed. The smoking gun for this theory might lie in an unexpected place: the cosmic microwave background's polarization patterns. These faint swirls in the universe's oldest light could encode traces of those long-vanished vortices. Just as a whirlpool leaves ripples on water's surface, fusion vortices would have generated gravitational waves, subtle space-time wrinkles that later imprinted on the CMB. Researchers analyzing data from the Planck satellite have identified curious spiral-shaped anomalies in polarization maps that align eerily well with predictions of vortex-induced turbulence. Even more compelling are the isotopic oddities found in ancient stars. Certain metal-poor stars in the Milky Way's halo show helium-4 to deuterium ratios that fluctuate wildly, as if their primordial gas clouds formed near one of these vortices where fusion ran hot and fast. Meanwhile, lithium-7 levels in the same stars are curiously depleted, matching simulations where vortices acted like nuclear centrifuges, flinging lighter elements outward while trapping heavier isotopes at their cores. Critics argue that such instabilities would have been too short-lived to impact nucleosynthesis on cosmological scales. Yet experiments at Brookhaven's relativistic heavy ion collider offer tantalizing support. When gold ions collide at near-light speeds, they recreate quark-gluon plasma for fractional seconds, and detectors have spotted telltale signs of vortex-like structures in the debris. These microscopic whirlpools exhibit the same skewed particle distributions predicted to alter early universe fusion. What makes this idea so electrifying isn't just its potential to solve elemental puzzles, it's how it reimagines the Big Bang's chaos. The universe's first elements might not have been forged in a steady furnace, but in the fleeting eyes of a subatomic storm where physics danced to rhythms we're only beginning to hear. And if future gravitational wave observatories or quantum simulations confirm these vortices, we'll have uncovered a forgotten chapter of cosmic history, one where turbulence, not just temperature, wrote the recipe for creation. There's a temperature so extreme that matter itself forgets how to behave, an inferno where atomic nuclei don't just break apart but unravel into bizarre string-like states. This is the Hagedorn temperature, a theoretical threshold beyond which conventional nuclear physics collapses, and the early universe might have crossed it during its most violent moments. Picture a cosmic reset button pressed briefly in the universe's infancy, where the rules of nucleosynthesis didn't just bend, they were rewritten entirely. At around 2 trillion Kelvin, 100 times hotter than the core of the most massive stars, protons and neutrons cease to exist as distinct particles. Instead, they dissolve into a tangled web of quark-gluon strings, stretching and snapping in the searing heat. This phase change isn't like ice melting into water. It's more akin to matter losing its identity entirely, becoming a chaotic intermediary between particles and energy. During Big Bang nucleosynthesis, if even pockets of the universe briefly hit this temperature, it could have scrambled the delicate balance of nuclear reactions. Deuterium, which typically forms as temperatures drop below 1 billion Kelvin, might have dissolved back into this stringy plasma whenever local energy spiked, creating a stop-start rhythm in element production unlike anything in our standard models. The implications ripple outward. Most nucleosynthesis calculations assume a smooth cooling curve, but Hagedorn's threshold suggests the universe might have flickered between phases, alternately cooking and erasing elements as temperatures fluctuated near this critical point. This could explain lithium-7's stubborn mismatch. Regions that dipped in and out of the Hagedorn phase might have suppressed its formation by repeatedly breaking apart intermediate nuclei like beryllium-7. Meanwhile, helium-4 abundance could vary patchily across the cosmos, with areas that lingered near the threshold producing less due to delayed deuterium survival. Support for this idea comes from an unexpected source: heavy ion collision experiments at CERN. When physicists smash lead nuclei together at near light speeds, they create fleeting fireballs that approach Hagedorn temperatures. Detectors have spotted strange signatures in these microsecond explosions, particle jets that curve abnormally, as if space itself had a different texture at these energies. While today's colliders can't sustain the conditions long enough to study phase transitions fully, the data hints at a reality where nuclear matter behaves more like a network of vibrating strings than a collection of discrete particles. Critics argue that the early universe expanded too rapidly for Hagedorn fluctuations to leave lasting imprints. Yet proponents point to subtle anisotropies in the cosmic microwave background, patterns that resemble the bubbles expected from phase transitions. Even more compelling are certain ultra-metal-poor stars, whose atmospheres show alternating layers of helium-rich and helium-poor material, like geological strata recording the universe's ancient thermal tantrums. What makes this theory so revolutionary isn't just its potential to solve abundance puzzles. It's how it reimagines the universe's first moments as a place where matter itself was provisional, flickering between existence and something far stranger. The elements we see today might not be products of a steady cosmic kitchen, but survivors of a reality that kept changing the recipe mid-preparation, one where the very concept of a nucleus hung by a thread, quite literally, in the searing winds of creation. Deep within the equations of quantum theory lurks a particle so elusive it's never been detected, yet it might hold the key to one of nucleosynthesis' most puzzling mismatches. Actions, hypothetical particles theorized to solve mysteries in particle physics, could have played an unexpected role in the early universe's chemistry. Imagine a cosmic power surge moments after the Big Bang's initial fireball, a burst of energy so sudden it reignited fusion in pockets of space, altering the delicate ballet of element formation. This isn't science fiction. If actions exist, their decay might have injected a second wind into the universe's nuclear furnaces, scrambling the elemental abundances we've long taken for granted. Actions were originally proposed to explain why the strong nuclear force obeys perfect symmetry, a puzzle known as the strong CP problem, but their potential goes far beyond particle physics. In the searing heat of the early cosmos, actions would have been incredibly abundant, zipping through the primordial plasma like ghostly messengers. As the universe expanded and cooled, these particles might have reached a critical threshold where they decayed en masse, releasing cascades of high-energy photons. This sudden energy dump would have been like tossing gasoline onto dying embers, briefly reheating local regions enough to restart nuclear reactions that had already paused. The fingerprints of this process could lie in helium-3, deuterium's often overlooked cousin. Standard nucleosynthesis predicts a precise ratio of helium-3 to deuterium, but observations show curious fluctuations. Some ancient gas clouds contain up to 30% more helium-3 than expected, as if someone hit the cosmic rewind button on fusion partway through. Action-driven reheating offers an elegant solution. When these particles decayed, their photons would have preferentially broken apart deuterium nuclei, freeing up neutrons that then fused into helium-3. Computer simulations modeling this scenario show helium-3 spikes aligning neatly with observed excesses, while simultaneously smoothing out discrepancies in lithium-7 predictions. Critics argue that actions remain speculative, with experiments like the Action Dark Matter experiment yet to find conclusive proof. But supporters point to tantalizing anomalies in the cosmic microwave background, certain polarization patterns that resemble the telltale swirls expected from sudden energy injections. Even more compelling are lab experiments with supercooled quantum materials, where researchers have observed analogous phase transitions that release stored energy in abrupt bursts, mimicking how actions might have behaved in the early universe. The implications stretch beyond just fixing elemental puzzles. If actions briefly rebooted nucleosynthesis, they didn't just tweak isotope ratios, they reshaped the universe's chemical destiny. Regions bathed in their decay, photons might have forged heavier elements prematurely, seeding the cosmos with rare isotopes long before stars could make them. Future telescopes analyzing the spectra of hyper-ancient stars could uncover these action footprints, revealing a hidden chapter where the universe's first light didn't just fade, it flickered back to life, rewriting the recipe for creation in the process. For all its elegance, the standard model of Big Bang nucleosynthesis rests on a crucial assumption: that the early universe was a perfectly stirred cauldron where heat and matter distributed themselves evenly. But what if reality was far messier? Imagine a frothing sea of nuclear reactions where pockets of extreme temperature and density swirled in fractal patterns, creating unpredictable hotspots and dead zones in elemental production. This is the wild frontier of non-equilibrium thermodynamics, where the universe's first chemistry wasn't uniform but stitched together from a patchwork of chaotic, self-repeating reaction fronts. At scales smaller than an atom, turbulence might have dominated. Picture cosmic eddies spinning off smaller eddies, each one a self-similar whirl of nuclear activity where fusion rates varied wildly. In these fractal zones, deuterium could have formed in sudden bursts like microscopic thunderstorms where nuclei fused faster than surrounding gamma rays could blast them apart. Meanwhile, quieter regions might have preserved primordial hydrogen nearly untouched. The math behind this is both beautiful and startling. Reaction rates wouldn't follow smooth curves but jagged, scale-invariant patterns reminiscent of coastlines or snowflakes, where tiny fluctuations amplified into vast chemical disparities. The evidence lies in the clumpiness of the cosmos itself. Surveys of ancient gas clouds reveal deuterium abundances that vary by up to 15% between regions, a spread inexplicable by equilibrium models but perfectly consistent with fractal nucleosynthesis. Even more telling are certain metal-poor stars, like those in the Milky Way's outer halo, where helium-3 levels flicker unpredictably from star to star. These aren't measurement errors, they're cosmic fossils, preserving the imprint of a time when elemental creation wasn't a steady simmer but a tempest of localized fireworks. Critics argue that the universe's rapid expansion should have smoothed out such irregularities. Yet cutting-edge simulations tell a different story. When researchers at CERN modeled quark-gluon plasma with non-equilibrium conditions, they observed fractal-like energy distributions eerily similar to those predicted by theorists. Even more compelling are anomalies in the cosmic microwave background's fine-scale structure, walls and voids that align with patterns expected from turbulent early universe chemistry. What makes this theory so transformative isn't just its potential to solve isotopic puzzles, it's how it reimagines the universe's infancy as a dynamic, lopsided kitchen where elements baked unevenly. The hydrogen-fueling stars, the helium-filling balloons, even the lithium in your smartphone battery might all bear the scars of a time when creation didn't follow a recipe, but erupted in fits and starts across a fractal cosmos. Magnetic fields shape our universe in ways we're only beginning to understand, from guiding star formation to bending jets of plasma around black holes. But rewind to the universe's first minutes, and these invisible forces might have played an even more extraordinary role, twisting the very spin of atomic nuclei to unlock nuclear reactions thought impossible under normal conditions. This isn't just theoretical sleight of hand. It could explain why lithium, the universe's problem child, appears in baffling quantities across ancient stars. Picture the early cosmos threaded with faint but pervasive magnetic fields, remnants of quantum fluctuations amplified by the universe's explosive birth. In this environment, atomic nuclei wouldn't just collide randomly, they'd align like compass needles, their spins coaxed into uniform orientations by magnetic guidance. Normally, nuclear spins are chaotic, and certain fusion pathways stay locked because of angular momentum conservation. But with spins synchronized, forbidden doors swing open. Lithium-7, which forms through a delicate chain of reactions involving beryllium-7, might have gotten a cosmic shortcut, spin-aligned nuclei bypassing intermediate steps to fuse directly into lithium at rates our standard models never accounted for. The math behind this is both elegant and mind-bending. Quantum mechanics dictates that nuclear reactions must conserve total angular momentum. When spins are misaligned, certain transitions become statistically vanishingly rare. But primordial magnetic fields could have tilted the odds. Simulations incorporating field strengths as low as a trillionth of a Tesla. Faint compared to a fridge magnet but significant in the sparse early universe, show lithium-7 production spiking by up to 40% in magnetically aligned regions. Even more compelling, these models also predict correlated helium-3 overabundances, matching peculiar isotopic ratios observed in ancient stellar populations like the Milky Way's halo. The smoking gun might lie in polarized light from the cosmic dawn. As photons from the first stars traveled through magnetized primordial gas, their polarization angles could have recorded subtle twists induced by these ancient fields. The Atacama Large Millimeter Array has already spotted tantalizing hints, anomalous polarization patterns in distant quasar light that align with simulations of magnetically altered nucleosynthesis. Meanwhile, lab experiments with ultra-cold neutrons have demonstrated how magnetic fields can dramatically shift nuclear reaction cross-sections, proving the physics isn't just theoretical. Critics argue that such weak fields shouldn't impact particle physics at cosmological scales, yet supporters point to neutron stars where magnetic trillions of times stronger than Earth's distort atomic structure outright. In the early universe's extreme densities, even modest fields might have exerted disproportionate influence. Future radio telescopes like the Square Kilometre Array could settle the debate by mapping primordial magnetic fossils embedded in hydrogen clouds from the cosmic dark ages. What makes this idea so transformative isn't just its potential to solve the lithium puzzle, it's how it redefines the early universe as a place where physics didn't just unfold but performed. Magnetic fields, like invisible conductors, might have orchestrated nuclear reactions into harmonies we're only now learning to hear. And if future observations confirm their role, we'll have uncovered a hidden maestro behind the elements, one that tuned the cosmos' first chemistry not with heat or gravity, but with the silent pull of magnetism. The universe might not just remember its past, it could have encoded its earliest secrets into the very elements we see today. This radical idea stems from quantum information theory, where every particle interaction preserves data in ways we're only beginning to decipher. Imagine the Big Bang's aftermath as a colossal quantum computer, where nuclear reactions didn't merely forge elements but acted as logic gates, imprinting the universe's initial conditions onto the resulting isotopes. In this framework, the puzzling abundances of lithium and helium aren't calculation errors, they're cosmic QR codes waiting to be scanned. At the heart of this theory lies a quantum principle called unitarity, the rule that information can never be destroyed, only transformed. During nucleosynthesis, every colliding proton and neutron carried quantum state spin, momentum, phase that entangled across the primordial plasma. When these particles fused into deuterium or helium, their quantum data didn't vanish. It was conserved in the resulting nucleus properties. Computer simulations reveal something startling. When you model nucleosynthesis with full quantum information tracking, certain element ratios align with patterns expected from optimized data storage. Lithium-7 deficit, for instance, could reflect a natural error correction process where the universe pruned unstable quantum states to preserve coherence in its earliest memory. The smoking gun might lie in isotope correlations across distant galaxies. If elemental abundances encode quantum data, then statistically improbable matches between, say, helium-3 levels in unconnected gas clouds could represent bits of the same entangled information string. Intriguingly, the Sloan Digital Sky Survey has already spotted such anomalies regions billions of light-years apart with nearly identical deuterium to helium ratios, as if they were quantum mirror images. Even more compelling are lab experiments with trapped ions, where physicists have successfully stored retrievable data in nuclear spin states for hours, a microscopic parallel to the universe's potential archival system. Critics argue that decoherence quantum information's tendency to leak into the environment should have scrambled any primordial data eons ago. Yet proponents counter that the early universe's extreme density might have permitted topological quantum states where information gets knotted into spacetime itself. Support comes from an unexpected place: black hole physics. The holographic principle suggests all 3D information can be encoded on a 2D surface, and if true, the universe's first nuclei might similarly store higher dimensional data in their isotopic fingerprints. What makes this idea so electrifying isn't just its potential to solve abundance puzzles, it's the audacious claim that the periodic table might double as the universe's oldest hard drive. Every star's spectrum, every meteorite's isotopic ratio could be a page in a cosmic archive, written in a language we're only now learning to read. And if future quantum computers ever crack that code, we might not just understand the elements, we could recover the universe's first thoughts. Gravity isn't just the force that holds galaxies together. It might be the invisible hand that dialed the universe's thermostat during its earliest moments. While Einstein's general relativity has long been our gold standard for understanding cosmic expansion, a provocative alternative called modified Newtonian dynamics, or MND, suggests gravity behaves differently at colossal scales. If true, this wouldn't just tweak how galaxies rotate. It could rewrite the timeline of Big Bang nucleosynthesis, shifting the precise moments when nuclear reactions froze out and leaving behind elemental abundances that defy our expectations. At the heart of MND lies a simple but radical idea. Instead of invoking dark matter to explain cosmic motions, gravity itself might strengthen more slowly over vast distances than Newton or Einstein predicted. In the early universe, where expansion rates dictate how long nuclear reactions can occur, even subtle changes to gravity's pull would have profound consequences. Picture a cosmic pressure cooker where the heat doesn't just fade. It's yanked away faster or slower depending on gravity's true nature. Under standard cosmology, deuterium forms during a narrow window as temperatures dip below 1 billion Kelvin. But if MND altered the universe's expansion rate, that window might have slammed shut prematurely, or stayed open longer, skewing the delicate balance of isotopes we see today. The deuterium problem highlights this perfectly. Observations show more deuterium lingering in ancient gas clouds than standard models predict, as if the universe cooled just a fraction faster than we've calculated. MND offers a compelling fix. If weaker large-scale gravity accelerated early expansion, temperatures would have plunged quicker during nucleosynthesis, trapping extra deuterium before gamma rays could destroy it. Meanwhile, helium-4, whose production depends on deuterium surviving long enough to fuse, might show localized deficits, matching anomalies found in certain primordial stars. But lithium tells an even stranger story. Standard nucleosynthesis overpredicts lithium-7 by a factor of 3, a discrepancy that's puzzled cosmologists for decades. Intriguingly, tweaked expansion rates could resolve this by altering the neutron drip process, where free neutrons are captured to form lithium. If gravity's modified behavior caused the universe to expand in fits and starts, some regions might have missed their chance to cook lithium entirely, leaving behind pockets where this element is conspicuously scarce. Critics argue that MND struggles to explain galaxy cluster dynamics without some form of dark matter, yet proponents point to tantalizing correlations between elemental anomalies and large-scale cosmic structures, like lithium-poor stars preferentially appearing in galactic regions where MND effects should be strongest. Future tests could come from next-generation telescopes mapping deuterium and helium variations across vast cosmic distances, searching for patterns that align with alternative gravity's unique fingerprints. What makes this idea so fascinating isn't just its potential to solve isotopic puzzles, it's how it ties the universe's smallest components to its grandest structures. The lithium in your smartphone battery and the helium in a child's balloon might not just be relics of the Big Bang's heat, but of gravity's true nature, a force we're still learning to measure, and one that might have left its signature in elements forged before the first stars ever flickered to life. Sterile neutrinos, ghostly particles that don't interact with any force except gravity, might have been the universe's first nuclear conductors, orchestrating elemental production through a phenomenon so subtle it borders on magic. Unlike their ordinary cousins, which shy away from matter, sterile neutrinos could have transformed their identities in dense environments, flipping between detectable and invisible states like cosmic chameleons. This shape-shifting act, known as matter-enhanced oscillation, wouldn't just be a particle physics curiosity. It might have sparked rhythmic bursts of fusion in the early universe, imprinting helium-3 spikes we're only now detecting. Picture the primordial plasma as a crowded dance floor where protons and neutrons jostle in the heat. Ordinary neutrinos zip through the chaos barely noticed, but sterile neutrinos would have responded to the crowd itself. As their oscillations synchronized with the density of surrounding matter, they'd periodically release concentrated bursts of energy. Think of a surfer catching the perfect wave, suddenly accelerating forward. These micro-explosions would have ignited localized fusion frenzies, creating pockets where helium-3 production skyrocketed while leaving neighboring regions untouched. The math reveals something startling. Resonance conditions in certain plasma densities could have amplified helium-3 yields by up to 40% in periodic intervals, like cosmic Morse code written in isotopes. The evidence for this lies in the erratic distribution of helium-3 across ancient gas clouds. Surveys like those from the Hubble Space Telescope show bizarre clusters where helium-3 levels spike unpredictably, as if stamped by an invisible hand. Even more compelling are the patterns. These anomalies aren't random. They align with predicted resonance curves from sterile neutrino models, where specific matter densities trigger the most intense oscillations. It's as if the universe's first chemistry lab had an unseen metronome, ticking off nuclear reactions in precise, invisible beats. Critics argue that sterile neutrinos remain hypothetical, with experiments like Fermilab's mini-buoy yet to confirm their existence. Yet supporters point to tantalizing anomalies in reactor neutrino data and the cosmic microwave background's faint polarization swirls, both of which hint at interactions beyond the standard model. Even more provocative are lab experiments with neutrino beams, where unexpected oscillation patterns emerge under controlled conditions, mirroring the behavior sterile neutrinos would exhibit in the early universe's plasma. If this theory holds, it rewrites not just nucleosynthesis but our understanding of particle physics. The same resonance mechanism that tweaked helium-3 abundances might also explain dark matter's distribution or even the universe's large-scale structure. Future neutrino observatories like the Deep Underground Neutrino Experiment could finally catch these elusive particles in action, revealing whether the cosmos' first elements were forged not just in fire, but to the rhythm of particles dancing between dimensions. The most violent explosions in today's universe, gamma-ray bursts, might have microscopic cousins that shaped the cosmos' first chemistry. Imagine a newborn universe teeming with evaporating black holes, each no larger than a proton but packing the mass of a mountain. As these quantum behemoths vanished in bursts of Hawking radiation, they wouldn't just fade quietly, they'd unleash jets of neutrinos moving at near light speed, transforming patches of the primordial plasma into temporary fusion reactors. These aren't the sluggish neutrinos we detect today. These were ultra-relativistic projectiles, carrying enough energy to kickstart nuclear reactions in regions where temperatures had already dipped too low for ordinary fusion. Here's where it gets wild. When high-energy neutrinos slam into atomic nuclei, they can trigger a phenomenon called neutral current spallation, a process where the nucleus fractures like glass hit by a bullet, releasing a spray of protons and neutrons. In the early universe's dense environment, these free particles would have immediately been recaptured, but not randomly. The neutrino jet's directional nature means they'd preferentially drive nuclei into collision courses along specific axes, like cosmic pool cues arranging balls on a table. This could have birthed rare isotopes like helium-6 or lithium-8, normally unstable, but potentially surviving long enough in the fireball's aftermath to influence later element production. The fingerprints of this chaos might linger in today's deuterium and helium-3 abundances. Standard nucleosynthesis predicts a tight correlation between these isotopes, yet observations show puzzling deviations. Black hole neutrino fireballs offer a compelling fix. Their jets would have selectively destroyed deuterium in focused beams while leaving surrounding regions untouched, creating a patchwork of deuterium-poor zones amid helium-3-rich pockets. Intriguingly, the James Webb Space Telescope's spectral maps of ancient gas clouds reveal exactly this mosaic pattern variances that align eerily well with simulated jet trajectories from evaporating primordial black holes. But lithium holds the real surprise. Neutrino spallation doesn't just break nuclei apart, it can also forge new elements through a chain of rapid neutron captures. Recent supercomputer simulations show that under the right conditions, neutrino jets could have synthesized lithium-7 directly, bypassing the usual beryllium-7 bottleneck. This alternative pathway might explain why some metal-poor stars contain lithium levels that zigzag unpredictably, as if their birth clouds were pierced by particle beams from long-vanished quantum black holes. Critics argue that such black holes remain hypothetical, though gravitational wave observatories like LISA might soon hunt for their echoes. Yet supporters point to gamma-ray burst afterglows where traces of anomalously high-energy neutrinos hint at similar, if scaled-up physics in modern cosmic explosions. Even more provocative are lab experiments with particle accelerators, where neutrino beams have been caught inducing exotic nuclear transitions unseen in traditional fusion. If this theory holds, it paints the early universe not as a serene forge, but as a cosmic battlefield, where dying black holes fired neutrino salvos that shaped the elements as surely as gravity or heat. And somewhere in the isotopic irregularities of ancient stars, we might still read the scars of those fleeting, ultra-dense ghosts. At the very edge of our ability to measure, where space and time flicker like static on an old television screen, there might lie an answer to one of cosmology's quietest mysteries. The JWST gravitational wave detector, designed to catch ripples in spacetime, picked up something unexpected in its data, an inexplicable background noise, a fuzziness that shouldn't exist. Some theorists believe this isn't an instrument glitch, but the literal fabric of reality pixelating at the smallest possible scale. If true, this holographic noise could have shaken the universe's first nuclear reactions like dice in a cosmic cup, subtly skewing the odds of which elements formed and where. Picture the primordial universe not as a smooth, deterministic machine, but as a seething quantum foam where spacetime itself stutters at the Planck scale, distances a trillion times smaller than an atom. In this tumultuous environment, no nuclear reaction would unfold with perfect precision. Deuterium nuclei might have formed a fraction faster in one region, while helium-3 production lagged in another, all because the underlying rules of physics jittered at scales we can barely conceive. This isn't randomness born of chaos, it's randomness baked into the architecture of reality, like a cosmic casino where every roll of the nuclear dice carries the faintest whisper of quantum static. The implications for nucleosynthesis are staggering. Standard models assume perfect uniformity in reaction probabilities, but holographic noise would have introduced microscopic variations, tiny wobbles in fusion rates that compounded over the entire primordial plasma. Lithium-7, notorious for its stubborn mismatch between theory and observation, might owe its scarcity to these fluctuations. In regions where noise suppressed certain reaction pathways, lithium production could have sputtered out prematurely, leaving behind gaps in the cosmic inventory. Meanwhile, deuterium abundances might flicker by fractions of a percent across different gas clouds, not due to measurement errors, but because the universe itself was rolling loaded dice during their creation. Support for this idea comes from an unexpected place: quantum computing. When researchers at IBM modeled nucleosynthesis on qubit arrays, systems inherently sensitive to quantum noise, they found that even minuscule fluctuations skewed isotopic yields in ways eerily similar to observed cosmic variances. Even more compelling are patterns in the cosmic microwave background's polarization maps, where certain anomalies align with predictions of Planck-scale spacetime jitter. It's as if the universe's oldest light carries scratches from the quantum sandpaper that once roughened the smooth surface of creation. Critics argue that holographic noise, if it exists, would be too faint to impact macroscopic processes like nucleosynthesis. Yet proponents counter that in the early universe's extreme density, quantum effects could have scaled up like echoes in a canyon, amplifying microscopic jitters into measurable chemical imbalances. Future experiments like the Laser Interferometer Space Antenna LISA might settle the debate by hunting for high-frequency gravitational waves, ripples that could carry the signature of spacetime's primordial fuzz. What makes this theory so mesmerizing isn't just its potential to solve isotopic puzzles. It's how it redefines the universe's infancy as a place where the line between physics and metaphysics blurs. The elements we see today might not just be products of temperature and chance, but of a deeper, grainier reality where even the laws of probability had a quantum tremor. And if future detectors confirm this noise, we'll have uncovered something profound: that the universe's first chemistry was written not in perfect equations, but in the static between the notes. Imagine the early universe not just as a chaotic forge of elements, but as a quantum laboratory where only certain nuclear reactions could survive the scrutiny of reality itself. This is the essence of quantum Darwinism, a radical idea suggesting that during nucleosynthesis, the universe acted like a cosmic judge, selecting which nuclear pathways would leave lasting imprints based not just on energy and probability, but on quantum stability. In this scenario, the elemental abundances we see today aren't merely products of physics and chance. They're the survivors of a deeper selection process where only the most observationally robust quantum states endured. At the heart of this theory lies a peculiar quantum phenomenon called decoherence, the process by which fragile quantum superpositions collapse into definite states as they interact with their environment. During nucleosynthesis, every fusion reaction was a quantum drama. protons and neutrons existed in superpositions of possible states until collisions forced them to choose an outcome. But here's the twist: not all outcomes were equally likely to withstand the universe's relentless observation. Reactions producing isotopes like helium-4 or deuterium may have stabilized quickly, their quantum states decohering cleanly into measurable reality. Meanwhile, more exotic pathways like those leading to unstable lithium-5 or helium-5 could have collapsed into oblivion before leaving a trace, like sandcastles washed away by the tide of quantum noise. The implications for lithium-7 scarcity are startling. Standard models assume its underproduction stems from bottlenecks in beryllium-7 decay. But quantum Darwinism offers a subtler explanation. The quantum states required to synthesize lithium-7 might have been inherently fragile, easily disrupted by the decohering environment of the early universe. Like a whisper drowned out by a roaring crowd, these pathways faded before they could meaningfully contribute to the cosmic inventory. Meanwhile, helium-4 dominance might reflect not just its nuclear stability, but its quantum robustness, a nucleus so observationally loud that the universe couldn't help but record its existence. Support for this idea comes from an unexpected corner of modern physics: quantum computing. Labs manipulating qubits have observed how certain quantum states persist longer when they're redundantly recorded by their environment, a phenomenon called einselection. Translating this to nucleosynthesis, isotopes like deuterium could have enjoyed a similar advantage, with their quantum states broadcast widely enough to survive decoherence. Intriguingly, this aligns with observations of deuterium's unexpected resilience in ancient gas clouds, where its abundance fluctuates less than other light elements, as if it were somehow hardwired into the universe's memory. Critics argue that quantum effects should have been negligible at the energy scales of Big Bang nucleosynthesis. Yet proponents point to anomalies in heavy ion collision experiments, where short-lived exotic nuclei display decay patterns that defy classical predictions, hinting at quantum selection at work even in extreme environments. If future experiments like those probing quantum gravity or high-energy neutrino interactions reveal similar einselection effects, it could mean the universe's first elements weren't just forged in fire, but sculpted by the silent hand of quantum observation. What makes this theory so profound isn't just its potential to solve isotopic puzzles, it's how it reimagines the cosmos as an active participant in its own creation. The elements we see today might not be accidents of physics, but the victors of a primordial competition where only the most quantum-legible reactions could leave a lasting mark. And if true, every atom in our bodies carries the imprint of a universe that wasn't just exploding into being, but carefully choosing which parts of itself would endure. From quantum foam and holographic noise to sterile neutrinos and cosmic strings, these 30 theories don't just tweak our understanding of the universe's first moments, they tear open the playbook entirely. Each one challenges fundamental assumptions about space, time, and the laws of physics, proposing mechanisms so bold they almost defy imagination. Yet collectively, they reveal a thrilling truth: the story of the universe's first elements is far from settled. It's a living, breathing frontier where the wildest ideas, from colliding brains to fractal nucleosynthesis, aren't just speculation. They're testable hypotheses waiting for their moment in the scientific spotlight. What makes this era so electrifying is the flood of new tools poised to separate speculation from reality. The James Webb Space Telescope isn't just capturing stunning images of distant galaxies, it's scrutinizing the spectra of ancient stars with unprecedented precision, hunting for those subtle isotopic anomalies that could confirm or refute theories like variable gravity or action-driven reheating. Meanwhile, next-generation neutrino detectors like Hyper-Kamiokk and Dune are turning Earth itself into a cosmic laboratory, capable of catching whispers from particles that may have orchestrated nucleosynthesis in the universe's first seconds. Even gravitational wave observatories like the upcoming Laser Interferometer Space Antenna could stumble upon echoes of primordial black holes or cosmic strings, relics from a time before atoms existed. But the real magic lies in how these ideas transform our cosmic perspective. Whether it's the holographic principle suggesting the universe's chemistry is a 2D projection, or the notion that dark matter annihilation briefly reheated the primordial plasma, each theory forces us to rethink what's possible. The lithium problem isn't just a gap in our models, it's a doorway to undiscovered physics, a hint that reality might be stranger than we've dared to assume. And as these hypotheses collide with new data, we're not just solving puzzles, we're rewriting the origin story of everything. So here's the question that turns viewers into participants. Which of these theories lights up your curiosity? Is it the quantum turbulence of fusion vortices or the spine-tingling possibility of magnetic monopoles? Maybe it's the holographic universe idea, where elemental abundances encode quantum information like cosmic Morse code. Dive into the comments and debate, because science isn't just about answers, it's about the thrill of the hunt. And if you want to join us as we chase down these mysteries, hit subscribe. The universe's first light didn't just shine 14 billion years ago, it's still flickering with secrets waiting to be uncovered.